Hello students, welcome back. We just completed section 1. They're basically about construction and fundamental properties. They're all about foundation. Next, let's talk about some further classification. First, algebraic versus transcendental numbers. A number alpha is called algebraic if it is a zero of a polynomial of integer coefficients. In other words, it can be written like this: an alpha to the nth power plus an minus 1 alpha to the n minus first power, and so on and so forth, all the way over to a1 alpha to the first power plus a0 equal to 0, where all the coefficient ai's are all integers. And set of all numbers like that are called algebraic numbers. And the largest class of number system is C, so we begin with complex numbers, but we can define the same thing for algebraic real numbers and algebraic complex numbers. That's why I think our textbook author left just alpha as a number, not necessarily a complex number. It could be real. Otherwise, we call the number transcendental. Here I use complex numbers, but you could do it for real as well. These are both real examples. E and pi are both known to be transcendental. Even though there are far more transcendental numbers than algebraic numbers, not many are known, to tell the truth. Here's an example problem. Prove that square root of 2 is algebraic. How do you prove that? Well, if it is a zero of a polynomial equation of integer coefficient, that's it. For example, what if you want to prove I is algebraic? Then all you need is this: x squared plus 1 equals to 0. Is that a polynomial equation with integer coefficient? Yes. So I is algebraic. Square root of 2 is irrational. Oh, that's a hard one. We'll do it later. Another classification: countable versus uncountable sets of numbers. It is known that N, W, Z, and Q are countable. In other words, they're all infinite sets, but there's one-to-one correspondence between the set of natural numbers and all these. So they're all countable. Yet R and C are uncountable. So there are far more real numbers, the far more irrational numbers than rational numbers. Yeah, I should say that. Q is just countable, and R is uncountable. So overwhelming majority will be real numbers that does not belong to Q. So those are irrational. And as for algebraic versus transcendental, algebraic numbers are countable. Consequently, transcendental numbers are uncountable. Well, there are some examples. We'll consider those later. Q and N have the same cardinality, so Q is countable. N squared is countable and those kind of things. R is uncountable. Yeah, this one, I think you went through this already in this introduction to proof course. How about this one here? R squared and R. Is there one-to-one correspondence? Did you already go through this in introduction to proof class? Or is it something you're going to do in analysis? Well, either way, it's not going to be for us. This is number theory. Another classification, discrete versus dense set of numbers. W and Z are discretely distributed, so we have the next number to the left or to the right. Q and R and C are densely distributed. Between any pair of rational numbers, there is at least one irrational number. So if you have any pair, A is less than B, you see, without loss of generality, one is less than the other. Let's name A is the smaller one, then A, and then average of A and B. So we get that. So there is at least one irrational number there. And there is at least one rational number there, excuse me. Same idea works for real numbers as well. And this is not the only rational number in between, of course. I mean, this one divides the line segment 1 by 1 to 1. But for example, if you do it like this, you can divide the number line 2 to 1. You can divide the line segment 3 to 4. You can do various. But of course, the problem says just find one. So this is sufficient. I just wanted to tell you there are many more, infinitely many more. How about this? Every neighborhood of a complex number contains at least one other complex number. Okay, all right. These two, they're linearly ordered, so you have the concept of between. For complex number, you can't do that, so I use the term neighborhood. I think it's better to visualize this rather than using some algebraic or analytical expression. So for rational or real, suppose this is a line, we have A here, and then we have B there, and then there's at least one in between. It doesn't have to be precisely half. I can find other things as well, many more, infinitely many more. But at least one of them, I can algebraically express it as average A plus B over 2. I can do that, and that works for rational and also real numbers. For complex numbers, it doesn't work that way because it's not linearly ordered. We do things like this. Starting from any complex number, draw a circle. It's two-dimensional like that. And then no matter how small, we can find at least one more complex number there. And there's one, consequently there are infinitely many more, because if I take smaller radius, there's one there as well. And then if I take even smaller radius, and this one there as well, and then you're going to get a sequence of complex numbers converging in there. And also, if I take appropriate radius here, then you can find still another complex number there, and many, many more. So there's one, consequently there are infinitely many. In any case, they're all densely distributed. How about some example? Between any pair of rational numbers, there is at least one irrational number. At least one rational number, excuse me. Okay, all right. We went through that. Between any pair of real numbers, there is at least one real number. Okay, we went through that already. Taking the average. Between any pair of real numbers, there is at least one irrational number. How about that? Let's see. This idea here, it works for two rational numbers because A plus B over 2 is a rational number too. It works for real numbers too because a plus b over 2 is also a real number, but this one will not work, because how do you know this is irrational? In general, it is not. And how do you guarantee there is an irrational number there? That's a bit problematic, isn't it? We can use completely different argument. In the interval, open interval AB, there are uncountably many real numbers. Is that true? I mean, I know entire real number system R is uncountable. Is any interval uncountable? Well, yes. You can prove it graphically like this. So we have a set of real number as a line like this. And then we have an interval, a to b like this. And then you can project this up. I'm going to change the color, but this thing is not responding very well. Okay, I got it. Kind of like this. I wanted to draw a sectional circle. Anyway, you can have one-to-one correspondence, you see. Each point goes like this, go up. So green and red, we have one-to-one correspondence. And then from the center of this half circle, we can project like this. For all points on the line. So even in this small interval AB, there are uncountably many real numbers. There's one-to-one correspondence between this small open interval AB and entire negative infinity to positive infinity exactly this way. This is not the only way to prove it, but it's one way to show it graphically. So there are uncountably many real numbers. Among them, only countably many are rationals. Therefore, there must be many irrational numbers there. There are only countably many irrational numbers there out of uncountably many real numbers in this interval. So the rest must be irrational. So you can prove that using the countable versus uncountable business. The proof of the last statement is extremely difficult, and we are not going to attempt it here in this course. We're going to do it in analysis. Between any pair of real numbers, there is at least one rational number. That's much harder. Okay, all right. That concludes section 2, and we're going to cover section 3 and section 4 in a separate video.